Welcome to the deep dive. Today we're looking into ion exchange chromatography, IEX for short.
hmm
It's this really smart way to separate molecules just based on their electrical charge. Super important for purifying proteins, nucleic acids, even cleaning water sometimes.
It really is a workhorse technique. We've got a good overview here, hitting the principles, the components, how it works, where it's used, the pros, the cons.
Right, and our mission basically is to get a solid handle on why IEX is so useful, what makes it tick.
Exactly. And at its core, it's all about electrostatic attraction. Think of it maybe like tiny magnets sorting metal filings. But here, it's charged molecules sticking to charged surfaces.
Okay, so the surface,
Yeah.
that's the stationary phase. Our source calls them ion exchange resins, little beads, right? With charged bits stuck onto them.
Yep, insoluble beads with covalently attached charged functional groups. And there are two main flavors.
Cation and anion exchangers.
That's it. Cation exchangers have a negative charge, so they grab positive molecules, cations. Anion exchangers are positive, so they bind the negative ones, the anions.
Gotcha. Like molecular Velcro, but one type likes positive, the other likes negative.
A good way to think about it. And then within those types, you have strong and weak versions.
Strong and weak. Okay, what's the deal there? Is it about how tightly they grab?
It's more about how reliably they hold their charge, especially when the pH, the acidity, changes.
Hmm.
Strong exchangers. They have groups like sulfonic acid for cation exchange. Think source S or sp-cephorose.
Okay.
These sulfonic acid groups, they're always negatively charged pretty much regardless of the pH. They're strong acid C.
Ah, okay, so they're dependable charge-wise, and the strong anion ones.
Those use quaternary ammonium groups,
Hmm.
like source Q or Q-cephorose. Again, they keep their positive charge over a really wide pH range. Very stable.
Okay, so strong means stable charge. What about the weak ones then?
Weak exchangers are more fickle. Their charge depends much more on the pH. Weak cation exchangers often use carboxylic acid groups, like in CM cellulose.
Same as Sheila's, right?
Carboxylic acid is a weak acid, so at low pH, it holds onto its proton and loses its negative charge.
So it stops being sticky for positive ions if it gets too acidic.
Precisely.
Yeah.
And similarly, weak anion exchangers, often using amino groups like DAE cellulose,
DAE, yeah, I've seen that one.
they lose their positive charge at high pH when it gets more alkaline. So with weak exchangers, pH becomes a really powerful tool to control the binding and release.
That makes sense. You can tweak the conditions. So that's the stationary phase, doing the grabbing, what's carrying the sample through. The mobile phase.
Correct. That's your buffer solution.
Hmm.
And its properties are absolutely critical, specifically the pH, which we just talked about,
Yeah.
and its ionic strength.
Ionic strength. That's like the saltiness, basically.
Sort of, yeah. It's the concentration of ions in the buffer. If you have lots of other ions floating around high ionic strength, they compete with your target molecules for the charged sites on the resin.
Ah, competition.
Right. So for binding, you typically want low ionic strength. It lets your target molecule interact strongly with the resin without much interference.
Okay, so step one, load the sample in a low salt buffer. Everything you want sticks. Step two, get it off again. Elution. How's that work?
Two main ways. First, you can gradually increase the ionic strength. Add more salt to the buffer flowing through.
The salty tug of war you mentioned earlier.
Exactly. The increasing concentration of salt ions effectively outcompetes your bound molecules, pushing them off the resin and letting them flow out. It's often done as a gradient, slowly increasing saltiness.
Okay, more salt, less sticking. What's the other elution method?
Changing the pH. Remember how weak exchangers, and also many molecules like proteins, change their charge depending on the pH?
Yeah.
Well, you can change the buffer pH to a point where either your molecule loses its charge, or the resin loses its charge, or both. Either way, the attraction breaks down and the molecule elutes.
Clever. So you can use salt or pH to control who sticks and who leaves.
That's the essence of it, and it's incredibly versatile.
Our source lists protein purification, nucleic acids, charged metabolites.
Absolutely. For proteins, you exploit differences in their overall charge at a given pH or their isoelectric points of the pH where they have no net charge. You can fine-tune the separation beautifully.
And water purification, too. That seems different.
Same principle, just different targets.
Mm.
Water softening uses cation exchangers to grab calcium and magnesium ions, the hardness, and release sodium ions instead.
Hmm.
Deionization uses both cation and anion exchangers to remove virtually all dissolved ions.
Wow, okay. So the advantages seem pretty significant. High selectivity for charged stuff.
High binding capacity, the resins can hold a lot of material.
Versatile for different molecules. Scalable for industry. Sounds great. Any downsides?
Well, obviously your target molecule needs to be charged or able to be charged by adjusting the pH. That's fundamental.
Right.
It's also sensitive, as we said, to pH and ionic strength, so you need precise buffer control. And if you use a salt gradient to elute,
You might need to get rid of the salt afterwards. Desalting.
exactly, which adds another step.
Mm.
And the resins themselves, especially the high-performance ones, can be a bit pricey.
Fair enough. So wrapping up, ion exchange chromatography really leverages the basic property of electrical charge to provide a super powerful way to sort and purify molecules.
That's it in a nutshell. It's about controlling those electrostatic interactions. Hugely important in biotech, pharma, water treatment, many fields.
It really makes you think. We've just explored how charge, something so fundamental, is used for separation. It kind of sparks a thought. What other really basic intrinsic properties of molecules could we potentially harness? Maybe things like, I don't know, their precise size or shape beyond simple size exclusion, or maybe how they interact differently with polarized light. Could there be whole new separation techniques waiting there?
That's a really interesting question. Definitely food for thought about where separation science could go next.
Thanks for diving into the charge dynamics of IEX today.
My pleasure.
Join us next time on The Deep Dive.